بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, so this is now lecture 3 in chapter 4, and today we're going to talk about projection in space. We've talked about vectors, and we also introduced PCA when we talked about eigenvectors, but I think still there are some missing loops. Especially I felt this when we talk about the projection of the features on the principal components. So now, if I ask you some questions, what is the projection of a vector on another vector in space? Do you know what is it? Huh? So it's usually we do the perpendicular line on the other axis, on the vector, right? And how this is expressed in linear algebra? Huh? No. How do we express a projection in space? Not cross product. Do you know?
You mean mathematically?
Yeah. The dot product. Okay. We're going to review this. So I want you to understand this very well. That's another property of the dot product. We talked about the dot product. It makes kind of similarity between the two vectors. And another thing of dot product is also represent a projection of a vector over the other. Okay? And this is pretty much related to PCA about the projection of features. So we will understand this in detail today. And when I say why the covariance is used to select features, does this make sense? What? Yeah, why?
Because covariance expresses how one variable changes when we change the other variable.
Okay, and yeah, what does this mean?
So it allows us to choose one variable and manipulate it as it affects the other variable.
Okay, but we can have, the covariance can be different across different features. So how the covariance will help us to select? Do you have any idea? I think we talked about this. Okay, so this is one of the topics we're going also to discuss in today's lecture. And another thing, why features that are projected, in principal component. When we talked about PCA, I said that we are going to project the features on a vector, principal components. So does this really represent the original data? We make a complete transformation. Look, we multiplied like a vector by a matrix or a matrix by a vector, and we will get something completely different. But this new thing, why it is representative of the first one, of the original data? Do you have any clue? Usually when you transform the data, it may change properties, right? But now we're going to use this data to make prediction model on the original data, for example. It doesn't look straightforward. So I want you to think about these issues. And now I'm going to introduce these issues progressively. So this is my plan for today's lecture. Okay. So let me start by reminding about what is a projection in space. So I think this is a very simple example. Imagine that you have a 2D plot and you have a vector which is in red, the vector v. And when I say I would like to make a projection of the vector v on the x-axis, so it represents, I'm going to make a projection using this dashed line here. So it's the orthogonal to the x-axis, and this represents the contribution of this vector over this axis. So this vector here, it's 3 times the magnitude of the unit vector. And this is why it has the coordinate of 3. Okay, so if you look at this mathematically, it's basically the dot product between 3, 2, which is the vector in red, and the x-axis, which is expressed by 1, 0 as the unit vector. So making this dot product, we're going to find 3, which is here the magnitude of that vector. So this vector has like a factor of 3 as its importance with respect to the x-axis. Does it make sense? Okay, so the dot product v multiplied by u is 3. Measure the extent of v alignment along the x direction. And the projection formula confirms that all of the v's influence in the x direction is captured, resulting from in a vector along the x-axis, which is this vector. Now let's do the same thing if we want to make a projection on the y-axis. What is the y-axis? It's basically the unit vector 0 and 1. This is the y-axis, right? So if I make a projection here, it's going to be a factor of 2 over the y-axis. And this is basically the dot product between both. So the dot product, it represents a projection of the first vector on the second vector. So this is something you need to understand. Okay. And here, it's not only, it's the dot product of the unit vector. So we have taken here the unit vector over the y-axis and the unit vector over the x-axis. So what is the general equation here? The compact formula, the projection of v over u is v multiplied by u. This is the dot product. And u divided by the norm of u square is the unit vector. And this is just the same formula, but it's expanded. So this is the unit vector, and this is the dot product, okay, divided by the norm. So this will result into projection, as we have seen in this plot. And this is how we can do it in NumPy. Imagine that you have v and u, and we can do the projection not necessarily on the x-axis or on the y-axis. We can do it on any vector, a projection of a vector over the other. So if I take a vector v, np.array 3, 4, and a vector u here. So first of all, to make the projection, we're going to make the dot product v u divided by the dot product of u, which is the norm, multiplied by the vector u, which is exactly the same formula as here. Okay, and we can also do it, calculate the norm of u, and then make on the normalized vector u. It's basically the same thing, but written differently. Is it clear? So, yeah.
What's the benefit?
Yeah, we will come to this. I'm introducing now the concept, so you understand, and then we will see the benefit in the context of data science. So the objective here is to understand the concept of projection, as you already mentioned, and the projection of vector v onto a vector u involves finding the component of v. Look, component, so principal component. We will come to this later. Okay, finding the component of v that lies along the direction of u. So this is v, and if I make a projection, I have u here. So all what you see in green, it's called the component of v, the portion of v along the u axis. Okay, I didn't make it on the y-axis or the x-axis. I made one with respect to another. Okay, and we talked about the formula, and this is like the projection calculation. Okay, so it's basically the dot product here, as you already mentioned. We will find 2.2 and 4.4. So look, if you look at this value here, it represents 2.2 over the x-axis and 4.4 over the y-axis. Okay, and this represents the component of the vector v onto the vector u. Nice. And this is a clearer picture. Okay, and the dashed line here is basically the projection line. And this is the vector u. It's 1, 2. Okay, so it represents basically, we will have here the magnitude of v into this axis. Now, if I ask you something now, what does represent 2.2 and 4.4? What does 2.2 and 4.4 represent? I already mentioned, but just it's the coordinate of what?
The projection of V and U.
Yes, it's the coordinate of the component of the projection. When I project V over U, it's the coordinate on the x-axis and the y-axis. What is the coordinate of the projection on the u-axis? What is the coordinate of the projection on the u-axis?
Conceptually or
Yeah, from the figure here.
2.5?
No, look. Now, if we consider this is a unit vector, so it's we're gonna the coordinate will be just the length of this line.
Can you repeat that question?
Yeah, the coordinate now. This is the u-axis. Okay, if I take this as a unit and expose it, for example, this is 2 units of the u-axis and plus maybe 2 point something. It's just 1 point. It's like you have one dimensional. Okay, it's a point on this axis. The projection is just a point. This is the projection. It's 2 points on the xy coordinate. But if you consider only this vector as your coordinate frame, you can have one dimensional coordinate frame. It's only one axis. Okay, so we consider this is 0, and here we move along this axis. So it's with respect to this frame. Okay. Yeah, because usually a point, a coordinate of a point, it's related to a coordinate frame. Now, when I say 2.2 and 4.4, is with respect to what?
The whole XY plane.
Okay, let me explain you. Look at this room where we are right now. If I consider this point as 0, 0, so what is my position now? I am in the x-axis, so it's maybe y is 0, and I'm going to calculate the distance from this point to here, let's say 4 meters. So my position now is 4 meters in this coordinate frame, starting from this point. Now, if I say what is my position with respect to Ahmed, is it the same position? No. If I consider that Ahmed is the reference, I'm going to calculate the distance. I am 3 meters away of Ahmed. So I have a different position with respect to another reference. If you are the reference, I will have a position with respect to that reference. If there is another reference, I will have a different position. So a position is always with respect to a reference. By default, our reference is the xy coordinate frame. Now, if I change the reference and say, my reference will be this vector. Okay, this vector now is equivalent to Ahmed as a different reference. Okay, so xy coordinate, this is like the reference of the room. And this point or this vector, it's like a reference with respect to just another point. You see what I mean? Okay, so representation in space. Now, if I say, what is my position in the earth? I need to calculate my GPS coordinate. Okay? And my GPS coordinate is different from my position with respect to the wall. So, positioning systems are always represented under a certain reference frame. Okay? So now, when we talk, yes?
I just have a question. When we project something on something, the result always will be on top of the original one? The one we projected on? Or it differs?
Yes, now we said we want to make a projection of V onto U. This is our starting point. And this is going to be the orthogonal line over the blue axis. Okay, I want you to understand these terminologies right now. واضح ولا لا؟ Yes. Yes, yes. No, we talk now mathematics. We talk mathematics. I want you to understand the meaning of a projection. Later on, I'm going to use the meaning of a projection in data science. But mathematically speaking, a projection is represented by this orthogonal projection of a vector over the other. And what you see in the green line is like the contribution or the component of the vector V with respect to the vector u. Okay? And if I want to represent the projection into the xy coordinate reference frame, it's going to be 2.2 and 4.4. This is the same reference frame I used to represent vector v and to represent vector u. Now, if I tell you what is the position of the vector u with respect to itself, it's just 0 because it is the reference. Okay? And now, what is the position of the projection, which is in green with respect to the vector u? I'm going to calculate that distance, and it will be, for example, I don't know, 2.5, 2.4, depend on how it's going to be. Okay? So this is the concept of a projection over another axis. Because now I can make a two-dimensional space, another two-dimensional space. I can make an orthogonal line here, and I will consider this one is x prime and y prime, which is rotated with respect to the first one. Now, this is called the transformation frames in positioning. So this is something that we teach also in robotics, but it's pretty much related. It's geometry. This is geometry, okay, in two-dimensional space. Okay, so the role of projection in data science is very important. It's being used in PCA and also in TESNI. It's another way to represent complex NLP data, but we're going to talk about this later. Let's focus on the essentials. So let's apply again this to PCA. Last time you understand PCA 50%, and today we want to understand PCA 100%. We start with the same data, okay? And now you already have some knowledge about what we need to do. We have this data, which represent grades of 10 students in math, physics, chemistry, and English. So what is the next step? And we want to select the most representative features. What we need to do? We want to select the most representative features. What is the definition of the most representative features? No. They are features that are related or not related. No, forget about projection. Now we talk stats. No. The features that are important should they be related with each other, dependent on each other, or completely independent of each other? Dependent. So if they are dependent, it's like they are the same.
Independent features.
Yeah. You remember that we said that these features must be not correlated. We use the covariance. I asked you about the covariance in the beginning. But before even the correlation, what we should do when we have data like this? First step in data science, when you have a data set. Come on, we talk about this every day. Yeah.
Filtration?
No? Yeah, filtration. We assume that your data set is perfect right now. How much time we need to repeat it? Normalization, guys. We need to do, why we need to do normalization? Yes.
Avoid exploding values.
Yes, we talked about this many times. Normalization in dot product for the cosine similarity. You have already seen the impact of normalization, okay, to check the similarity between two vectors, right? So always, and they said this yesterday and the day before and last week, when you have a data that is not standardized, the first thing you need to standardize your data. All your data must be values between 0 and 1 or -1 and 1. That's a general rule. Otherwise, you will have trouble converging your data into a certain distribution. And this normalization will not change the characteristic of this data. Okay, because statistically speaking, from distribution perspective, it's going to be the same. So everything about data science is to maintain the distribution of data. توزيع البيانات. If you have normal distribution, exponential distribution, it must be the same. Because this is what matters. The value by themselves doesn't matter. It's the distribution of data that will allow me to make an estimation or a prediction. Is it clear? Okay. I know these concepts, are not easy to grasp, but these are foundation. When you do machine learning, first thing you will do with the data, normalization. And you must understand why. Because you're going to make many multiplication, many dot products. If you don't normalize, you're going to have plus infinity quite quickly. So I need to put this data down with zero mean and unit variance. The variance must be 1 and the mean must be 0. Okay? This is how we control it. And after that, we do the covariance matrix. Why the covariance matrix? To see the relation of between, no, not normalization, it's the relation between the different, now, math, physics, chemistry, are they related? If they are all related, I can take only one, or a representation of these. We don't want to have many features because our model will be more complex. We want to reduce this feature. This is what we call dimensionality reduction. We reduce the dimension of the feature space. Now, how many features I have? 4 features. So I say my feature space has a dimension of 4. Now, if all these features are completely independent, so they will contribute to the prediction model. If they are dependent, so we can reduce them. Why I have to work with 4 features that are related? Because their contribution to the model will be the same. واضح ولا لا؟ If you ask this one, provide you the same response as the others, you can only ask one to get the response, to get the prediction. Is this clear? I want this to make sense. And we measure this with the covariance. Now I can say there is a relation between math and physics 99%. معناها الجريدز في الماth, if he is good, the physics will be good. If bad, the physics will be bad. So it's basically the same thing with chemistry, and a little bit less with English. So now, in this kind of situation, one of the ways to reduce this data is to use principal component analysis, PCA. And we did this last time. What is the rule now? What we should do? I have a covariance matrix like this, and I want to select the component, and I say component, that has the highest variance. Okay, what is the technique now?
Normalization.
No. We convert this covariance matrix into eigenvalues and eigenvectors. Okay? This is what we did in Sunday. We did. This is the same example. I didn't do anything new right now. Okay? So this is what we call the eigenvalue decomposition. Because eigenvalues, I can transform this matrix that represents the correlation into diagonal matrix with lambda represent the eigenvalues. And we have learned that the dominant lambda represents the highest variance. And I want to check the component that has the highest variance. Okay? And I know what you don't understand right now. You don't understand why the highest variance will be the most representative. Do you understand why? You don't understand. Okay, why the highest variance component will be the most representative?
Maybe it will predict better since they're not related, so it will detect which is which.
Look, I will explain later. Let me go step by step. Okay. Now I think do you understand this step now? We calculate the covariance matrix, and we want to make an eigenvalue decomposition. Okay? Because the eigenvalue, and we learned this last time, it indicates the amount of variance carried by each component. Forget about why the variance is important. We will come to it later. And the eigenvectors define the direction. So we will have multiple vectors in space instead of the original representation in space. مثل ما عندنا an xy axis, and I want to find other type of vectors where I can make projection to reduce the dimension. This is the main idea about this. Okay, now in PCA usually this is the process. We calculate the covariance matrix as we did, and we decompose the covariance matrix to find the eigenvalues and eigenvectors, and then sort them out from the biggest value to the minimum value, and then select the top k eigenvectors that are the most dominant. These are the values that are going to give me the best information. Okay. Now, if we do the eigenvalue decomposition, and you can do this with Python, there is already, you can extract the eigenvalues and eigenvectors using this formula, and you will find these values. Lambda 1, 3.9, lambda 2, 0.03, lambda 3, 0.0037, and lambda 4, 0.016. And for every eigenvalue, we will have an eigenvector. We already talked about this. Okay? That's fine. Now, what is the most representative? What is the component that has the highest variance? Is the biggest eigenvalue by definition. You understand that, you don't understand. By definition, this has the highest variance. Okay. So I'm going to take this one. And now I will go back to my standardized data that I have made standardization. And I have my data set, which contains the values of the grades. Of course, they are standardized between -1 and 1. And I have the eigenvector that represent the dominant component. What I will do right now, I will make a projection of all these data into the principal component, the most dominant component. How can I make a projection? Using what? How do we make projection? Using? Yeah. We have seen in the beginning that the dot product makes a projection of one vector into the other. Now, this whole data set, I will make projection on the vector that has the highest variance, okay? And this will reduce this data set of 4 features into one vector with the same number of, so I have here 10 values. So this grade will be represented by one value on the vector, the eigenvector. The second grade will be represented by another value on the eigenvector. And the third value will represent by one, because I choose only one vector. I can choose 2 vectors if I want. So I make projection on this one. It's like I will have x, y coordinate. I make 2 projections, I will have 2 coordinates. But I made the thing simple. Okay? So this will reduce. Look now, I started with 4 features. I ended up with 1 feature. It's kind of magic, but it works. But still, let me come back to my question. We started from this data set. We transformed it to a standardized data set. And finally, of course, after doing the covariance matrix, we make eigenvalues, eigenvector. And finally, we have this data set. Is this the same as this? Why? Or you just believe what I'm saying? Maybe I'm saying something wrong. How can a data set like this be represented by just one vector? Think about it. عجيب ولا مش عجيب؟ شفت الآن؟ We started from this data set and say, if you want to make a prediction model on these features, you can use this one.
But can you go back to trouble?
No, but this is a summary of everything back. Forget everything I'm saying about. Yes.
So we said that the eigenvector is like a feature of the matrix. Is it the same as this case?
Yeah, this is what I'm asking. Why this is going to work to make a prediction model of this one? We made the first transformation, we made the second transformation, and we still say that this is representative.
No, I meant that if we could get the original matrix from the one that we produced, then
The original matrix.
yes.
Yeah, this is the original matrix. And I'm telling you now You can replace this matrix by this one, by just a vector.
The first one makes sense, but the other, I'm not sure why multiplying eigenvalues would make it the same.
The first one makes sense.
Yes, it's standard.
The second one is more weird, right?
So the projection of all the vectors into one vector.
Yeah, it's a projection. But is this projection representative? That's the question.
Is it because all of them are dependent on each other, so it just represents them by one?
They are dependent, not independent.
Yes, dependent.
Okay?
Yes. So representing them by one number makes sense because changing the value of one will change the rest. They all correlate
Yeah.
with each other.
What you're saying is somewhat makes sense. Because he said, your colleague said that since all these numbers are very much correlated, we can replace them with one vector. So implicitly this means, you understand what is a distribution of data or no? Probability. Every data, random, has a distribution. Can be normal distribution with a variance and a mean. Can be Poisson distribution, exponential distribution, or empirical unknown distribution. So as already mentioned several times, this is pretty much representative from statistical perspective of this data because it represents the same distribution of data, but in different spaces. علاش عملت لكم في space 2D 1D space, we can export it to 3D space if we want. It's the same data but expressed in different spaces. Usually a point in space, ما قلت لكم GPS coordinate is different from my point, but I'm in the same position. So it's the same data but represented differently in space. Now I use only one-dimensional space. I can take the second component and convert from four-dimensional space to two-dimensional space. I will have x and y axis. It's the same data, but represented differently. Now, did you get a little bit the information? It's geometry. Think about the points in geometrical frames. It's the same thing. Okay? So I represented now, instead of having four-dimensional space, one point represented in four axes, I will have this point projection into one axis. And surprisingly, it does the same thing because I use the axis that captures the most amount of information. Information in data science, it's captured by the variance. If I don't have variance, I don't have information. This is the information theory. Okay? Now, if, for example, I have students, all of them, they get 5 out of 5. All of them. It's the same data. Variance is 0, information is 0. Okay? Same performance. So the information is related to the amount of... There is no pattern. There is no pattern that I can learn to predict. Okay? Zero pattern. However, when I have diversity in the data, okay, this type of data is going to give me this type of output. This pattern is going to give me, because these patterns are random in reality. So this randomness, this is what represents a pattern in data science. Okay? Now, the pattern here is similar to the pattern here because they share the same variance. To some extent, not equal, but very close to each other. The distribution is close to each other. So the key point that this is valid, it's because variance is the information. This is a very important fact. PCA preserve the variance, which represent the most informative aspects of the data. The second thing, the principal component, what did we choose among the four eigenvalues, eigenvectors? The one that has the highest one. Imagine that I use the lowest one. It's not going to be a good representation, okay? Because the contribution is very small. Now, in this particular case, it's like all the data is mapped to only one axis, and I'm going to show you this clearly in a while. Okay? We talked about the covariance and so on. So, this is, now I took only two features, اللي هو الماth grade والphysics grade. just to make things simple. Now, if I take my data set and I will represent all the grades into XY coordinate. Math is X, Y is, so this is one grade of a student. He took this value, standardized value, minus 1.85, minus 180. And this one takes this one. Look at the grade. There, it's like a line. And we didn't see this from the data set, but when I represented this in 2 space, if I represent this into 3-dimensional space, we will find like we have a hyperplane. So, and now, this is the principal component. What you see in green is the principal component. And what we want to do is to project the original data into this axis. So, if I make a projection, do I lose too much information? Now, this point will be projected here, and this point will be projected here. You see? And the projection is done through what? The dot product. Okay? So now, I will say, instead of having 2-dimensional space or 4-dimensional space, I will take all my data into this line because it's very close to it. So, this component is going to represent, to a very good extent, the essence of my data. The information that is captured in my data.
Is the principal component the same as the dominant eigenvector? Or
Is the dominant eigenvector now in this case? I can have another eigenvector, but I didn't want to complicate things. I made only one. Okay? And look now, if I trace the whole line, so I will move from, instead of saying I have the coordinate, look at this point. Is 0.97, 0.91 in the xy coordinate. Look, it's almost at 1, 1. But now, if I make a projection, it becomes 1.52 on this axis only. I need only one value, by the way. You can see. So, instead of working with 2 values or 4 values, I will map this to the projection on that line. And there is no big difference, okay, with respect to the characteristic of the data when I make a linear projection. Usually, a linear transformation doesn't change the information of the data. So we are using this property in order to reduce the dimension to a lower space dimension without losing the information that is carried out by the data. شوية كلام فلسفي لكن that's the reality of science, probability and statistics. لأنه what we care about are not those numbers, we care about their distribution in space. So we're going to reduce the dimension of the space where they are represented into a smaller dimension to make the prediction easier. Because if I predict over a value, it's easier than I predict over 4 values. If these 4 values are not different, they are dependent, I don't need all of them. I need only one of them. But I make a combination, a good combination of them, so I don't lose that information. واضح? It's a different representation in a different space, in different frame. Yes, yes. Okay? But the most important thing, this is now the values that we have get, and they represent the coordinate on that line. Very simple. It's very simple. You make a projection, you change the coordinate system, you change your feature vector representation. But it's the same data.